Hello, and welcome to another section of the Data Structures and Algorithms course. In this particular section, we'll be focused on dynamic programming. And in this particular video, we'll be introducing dynamic programming to understand what exactly is dynamic programming and how does it allow us to have more efficient, recursive functions within your programming sort of challenges. So let's get ahead and get started. You'll notice that dynamic programming can simply be summarized as an algorithm that allows us to solve recursive problems, but we'd love to start this sort of explanation from scratch. So let's look at what we mean by recursion. So what exactly are recursive problems? So a recursive problem is a problem that involves smaller but similar and repeated subproblems, right? And I know most of you might already be familiar with recursion, but let's look at a typical example. One really common example that you might have come across are the Fibonacci numbers here. And just in general sense, the Fibonacci numbers is pretty much a sum of the previous two terms. Let's look at an example. If I had my first two terms at 0 and 1, then it means my third term is going to be 0 plus 1, which gives you 2 in that scenario. If I wanted to get my fourth term, I'll go ahead and do 1 plus 2 to give me 3. Now you already get the gist of it. It's always a sum of the previous two terms. So if we go to the fourth term, which is now the fifth term, it's going to be 2 plus 3 to give you 5. And this will continue all the way till whatever nth term you want to find. And there's one thing you'll see about the sort of Fibonacci number. The computation is very repetitive. At any given point, whatever you're calling is simply the sum of the previous two sums. But let's see how this sort of recursion will work in code exactly, because we'll tend to call recursion in code as a function that recalls itself, right? Because there's like a repetitive flow off of that. And let's do this practically. What would happen if we wanted to generate this sort of Fibonacci numbers by ourselves from scratch? So I'll create a function here called let's define Fibonacci, right? And this sort of function will only take one sort of entry here. So we'll just be taking n, which is going to be what sort of term do we want, right? So if we want the 100th term, that's what n is going to come up with. And just to be able to get this sort of clear thing, we already know that to return n in the simplest and basic of senses, it's pretty much a sum of the previous two terms. So the sum of the previous two terms will pretty much be similar to calling this sort of function again to find n minus 1, and then we'll add it plus Fibonacci n minus 2. So in simple terms here, what I'm saying is we are summarizing our entire problem by understanding that this function, we can simply summarize it as calling the two previous functions. So if I had Fibonacci 100, I would simply want it to go ahead and compute Fibonacci 99 plus Fibonacci 98. And then within that particular function, Fibonacci 98, it will compute the n minus 1 for it, which will be Fibonacci 97 plus Fibonacci 96. And once this function computes, this sort of sum will be attributed to this sort of function. Very, very simple. There's a caveat there in that we are always looking at the two previous terms, but when your sort of entry is 1 or 2, so if your n is 1 or 2, there's no two previous terms. So those are things we need to define off the boat automatically. So what we'll go ahead and do is we'll just add if statements to go ahead and say that if n is equal to 1, right, we'll go ahead there and return what that first term was for us, which in this case was 0. And then we'll also go ahead and have if n is equals to 2, we'll go ahead and return what we had already defined as our second term as well, once again, which was 1, right? And from n is equals to 3 onwards, we'll always have this sort of recursive functions being called out with utmost efficiency. There's just one sort of caveat I'd add here, just for the sake of efficiency here. In case we have an n that is less than or equal to 0, then we'll go ahead always and return none. It depends. At times, different sort of challenges would require you to define it differently. But here, I don't think there's a term whenever it's 0 or less than 0. That's just an error in that particular front. So I could return an error, or in this case, I'll just go ahead and return none, right? Times you can just go ahead and print a statement like that. That's what you could do. Like the you need to put in a positive number. But let me just do none for the sake of it. And this is very clearly simple. To get Fibonacci n, we're simply recalling that function twice for n minus 1 and n minus 2. But because we don't have two previous terms when n is equals to 1 and when n is equals to 2, we go ahead and define what we need to return in that particular float. So this is a simple example of how we see recursion in actual code. A function calling itself. So a function calling itself, that's what we call recursion, or if you want it in English terms, recursion is a problem that has repetitive sub-problems. So this is pretty much a repetitive sub-problem of the initial problem out there. So now let's go ahead and talk about the big problem with recursion. And this is what's going to get us to understand exactly why we use dynamic programming. So let's imagine we're taking Fibonacci 6, right? And let's understand what's happening under the code that we're running over here. So if we're getting Fibonacci 6, our function would have to go ahead and compute Fibonacci 5 plus Fibonacci 4. But whenever it's computing Fibonacci 5, it also has to compute Fibonacci 4 and 3. For whenever it's computing Fibonacci 4 and 3, you can see it has to compute Fibonacci 3 here, Fibonacci 2, and then for Fibonacci 3, it goes ahead. And you can see like for each and every single recursive function we have. So every time we're calling that particular function, there's subset functions that we have to keep calling. And this continues up until it's either Fibonacci 1 or 2 that we're computing, because those ones are the ones that do not have a sort of recursion underneath, because we have a clear number to be returned. So this is very, very essential here, that the problem, you can already see it from the graph we have here, is that we're doing Fibonacci 6, we have those sort of branches of what's going to be computed underneath. But the clear problem is we end up repeating function computations a lot of time. So for us to just get Fibonacci 6, we end up computing Fibonacci 2 about 5 times. Right? We end up computing Fibonacci 3 about 3 times, Fibonacci 4 2 times, Fibonacci 5 1 time, and then Fibonacci 6 another 1 time. And you can start imagining how wide these branches would be if we were just computing Fibonacci 100. How many times would you be computing Fibonacci 2? So the clear thing here is we have some sort of inefficiency. This repetition is great. It makes our sort of reading the function very, very easy, but it's not so great in regards to how much computation you're using, because you're repeating the same computation again and again. Okay, so let's talk about the problem of recursion, which should now be very clear. First of all, we are repeating computations, right? We don't want to recompute Fibonacci 2 100 times if we were to do Fibonacci 100. And what you'll realize is the number of operations, given that we have a tree-based structure there, actually doubles for every unit increase in n. If you've gone through our video on big O notation, you'll realize whenever you have whatever we've seen here with this sort of Fibonacci tree as well, this will tend to have a complexity of big O 2 to power n, because for each and every single n entry, we are doubling the amount of computations we're working with as well. So that's worth noting here. And we can easily avoid all this repetition by simply saving the solutions to the pre-computed functions. So what if the moment we tabulate Fibonacci 4, we save it somewhere so that next time we want to get Fibonacci 4, we just go ahead and call sort of the solution from a sort of saved dictionary. And that's what you're going to implement next, not a problem. And simply by saving the solutions, it would mean instead of repeating an operation like 100 times, you'd only do it once. So if you're doing Fibonacci 100, Fibonacci 99 will only be done once, Fibonacci 98 will only be done once. Each and every single sort of computation that is part of your recursion will only be done once. So instead of us having that sort of big O time complexity of 2 to power n, where the number of computations are doubling with every increase of n, we can simply reduce this to big O of n, right? And so from 2 to power n to n, because we are only going to compute all the different sub sort of functions once, because for us, whenever we call it again, we'll just be calling the solution that has already been computed from a set dictionary, right? And you'll start to see the efficiency of this. So let's imagine we just had Fibonacci of 20. With us saving the solutions, we'll only do, let's sort of 20 computations, right? So Fibonacci 20, 19, and the likes, we're saving them, we are calling them all across. But if we didn't save it and we left the code as it is at the moment, we'll be doing over 1 million sort of computations. This gets worse the moment your n gets higher. So at 100, you can see we're already doing 1.27 times 10 to the power 30. That's already a number I couldn't write on this particular slide. So by just saving your solution slightly, you're able to improve efficiency significantly, particularly when you think about that n becoming quite large. So let's go ahead and look at how we can add this sort of memoization, which is going to be a new term, to our Python code. So memoization, what I'm going to define it as, is a way for us to save what we've already computed and calling it the moment we need it again, so that we save ourselves the computational stress that comes with repeating the sort of recursive functions and recomputing them again. So this is going to be a very common sort of thing you understand whenever you work with dynamic programming. So let's go back to our code.